feedback in realistic environments.
All right, it's a pleasure to be here after 4 or 5 years again. And I'm going to be talking about Galaxies on Fire, where FIRE stands for feedback in realistic environments, as Joel said. And this is an effort with a large team. So this FIRE collaboration is mostly led by Phil Hopkins, Claude-André Foucher-Giguère, Elliot Quarter, and myself, and several postdocs and several students, as well as several close collaborators at CETA, Norm Murray, and at Irvine, James Bullock, and people scattered elsewhere. So I showed the pictures of people that either recently submitted or are about to submit papers related to our FIRE work. And this is Sasha Murato, DK Chen, Coral Wheeler, Cheng Ma, Jose Onyorbe, Robert Freca-Vandevort, and Daniel Angles-Alcazar. All right. So let's see what's going on with this feedback and what we want to learn about it. So for a long time, I looked into gas inflow. And the reason that this was interesting, and it's still interesting, is that the inflow of gas from intergalactic medium is needed to supply long-term star formation activity of galaxies. And this inflow is naturally present in cosmological models, and we see it in all simulations. The only problem is it's hard to observe. And it can be in cold mode accretion through filaments, it can be cooling of the hot medium, and it can be complicated stuff. But nevertheless, we see it in all kinds of simulations, SPA, JMR, moving mesh, but it's very hard to see. So we also know that in order to produce realistic galaxies, inflow is not good enough because it puts too much stuff into galaxies, and you end up with galaxies that are way too massive, and for the mass function that has very high low mass end and high mass end. So we need outflow of gaseous material from galaxies to regulate galactic growth. And outflows, on the other hand, are pretty easy to see observationally. We can see them at low redshift, such as this starburst case M82 in emission. And we can also see them observationally in high redshift in absorption lines. That's an example of stack profile of flight membrane galaxies at redshift 2.5, and you see blue shifted absorption from galaxies. So you see it all around, but it's actually pretty hard to model. You will see why. And the complication comes from the fact that outflows interact with the circumgalactic medium, and they do interact with the infalling gas as well. And they often recycle back into galaxies, as pointed out by Ben Oppenheimer and others. So to understand galaxy evolution, we need to simultaneously model gas inflow, gas outflows, and their complex interactions to figure out what exactly is happening and how do galaxies grow. So how to model star formation feedback in cosmological simulations? There's lots of text, but I'll guide you through it. We think that in low-mass galaxies, below about L star or similar, star formation-driven winds are the main outflow mechanism from galaxies. They likely dominate. The most obvious drivers that people talk about are supernovae, as pointed out by Avishai and others a long time ago. The problem with this is that at a typical resolution of cosmological simulations, supernova feedback tends to be very ineffective. It affects too much gas that is heated to too low temperatures, and it cools too fast without generating much momentum. So you end up having weaker feedback than you would like to just by supernovae alone. And there are two common methods to generate efficient outflow from galaxies to overcome this issue with relatively low resolution. The first one is so-called hydrodecoupling, in which we can implement winds by hand by literally just telling them how much mass loading they should have compared to star formation and tell them about the velocity they should be launched with. So this is clearly not predictive for the wind properties, but you might learn about IGM and properties of a galaxy as a population. These winds are then usually not allowed to interact with the gas within the ISM and close to galaxies until they leave the galaxy to produce efficient outflows. And this is the work done, this is the approach taken for almost all very large-scale cosmological simulations, except Eagle, which has a little bit more complicated approach. The second way is to prevent cooling. This is usually done in zoom-in simulations where you resolve some parts of the ISM, but you still don't get quite high enough resolution to avoid this overcooling of supernova remnant. And in this case, supernova feedback heats the surrounding gas, but this gas is not allowed to cool usually for 10 million or tens of millions of years, which is orders of magnitude longer than the actual cooling time of these remnants. And this allows the gas then to escape the galaxy and produce large-scale outflows. And this is done in high-resolution simulation. It can allow for bursty star formation, but this cooling prevention does not really allow for completely realistic treatment of the ISM and winds close to galaxies. So what is actually happening in interstellar medium, and can we do better than this? So we know that realistic gas can cool, and it also responds to hydrodynamics. It's not decoupled, and it does cool. So how can we enable winds to develop cell consistently and help us get towards the solution of galaxy formation problem? So from observations of the interstellar medium, we learned that there are multiple processes happening in star-forming regions. There is radiation pressure on dust, there is photoionization and heating, there are stellar winds that can heat and push the gas, there is photoelectric heating of the surrounding medium, there are supernovae type 2 that like to explode usually few or tens of million years later and affect the surrounding medium. And all of these can be important in different stages of the evolution of a star cluster. So what's happening around the star cluster will be determined by all of these things at different stages of the evolution. So we try to capture some of this complexity in the cosmological simulations of FIRE project. And here FIRE stands for feedback in realistic environment. And we try to simulate galaxies with a physical star formation model within the multiple ISM, where we take into account this complexity and still have galaxies in fully cosmological environment. So in FIRE, we resolve formation of giant molecular clouds. Often we don't resolve details of these clouds. But we do include range of these relevant feedback processes in addition to supernovae energy and supernovae momentum. The critical here with supernovae is that we also account for the momentum accumulated by supernova expansion in the case we cannot resolve the Settle-Taylor phase of the supernovae. So if our resolution is poor, if it drops to 20 parsecs or so, we need to account for the momentum push from the supernovae because we would get to the overcooling that supernova remnant is just not adding enough momentum to the medium. And the other critical thing is that several feedback mechanisms act before the supernovae explode, such that they lower local density and boost the efficiency of supernova feedback overall. So we can actually get large-scale outflow from galaxies without hydrodecoupling and without cooling prevention. And in current set of simulations, we use modern pressure SPH scheme that can do Kelvin-Helmholtz, Rayleigh-Taylor instabilities, and so on. And we are slowly switching to even better hydro schemes. So a little bit more details for aficionados. We allow gas to cool to below 1,000 Kelvin and allow star formation only in locally self-gravitating gas, typically at physical densities of 100 particles per cubic centimeter, sometimes 10 in lower resolution cases. And most of these simulations are highest resolution zooming cosmological simulations to date. In dwarfs, we can reach few hundred solar masses per gas particle. And in Milky Way size halos, we are usually at 10 to the 4 solar masses per particle. And resolution is varying from few to few tenths of parsecs, hydro resolution in the dense part of ISM. In the halos, our resolution is typically much poorer. And the energy and momentum input that we are adding to the surrounding is based from Starburst 99 stellar population synthesis model, and we follow distribution of supernovae 1A from other models and so on. So the goal of this relatively complex feedback scheme in high-resolution simulations is to understand how does the local feedback affect galaxy evolution and the cycle of baryons. Can we learn something more than before? So first check was to see if we are getting stellar masses of galaxies that make any sense. So we need comparison with observations directly to test the model because we did not tune the parameters. The input comes from stellar population synthesis, and some of these things will likely be wrong. But the good thing is that the stellar mass-halo mass relation, which is marked by these points here, representing different simulation, and these lines are different observational estimates, seem to be in good agreement with observations. There might be some deviations at some particular cases, but these are zoom-in simulations, so we don't have good enough statistics to do much more detailed comparison, but it's in good agreement with observation. In our simulation, cover halo masses from around 10 to 9 solar masses to close to 10 to 13 solar masses. So from ultra-faint dwarfs to usually something more massive than the Milky Way. We are also having pretty good mesh to star formation histories of galaxies that typically has been an issue in these kind of simulations. So I wanted to point out before proceeding of what we can actually do with FIRE is that it's critical to include a range of feedback mechanisms. Because these different feedback mechanisms that operate in star-forming region, they couple non-linearly. For example, if you look at these points here that represents the same dwarf galaxy, these different symbols represent what happens when we include or exclude different kinds of feedback mechanism. And you just cannot add them simply to get the final solution or to get the final suppression of what is happening at the end. So you need to include all of these because pre-processing of the surrounding medium will change the outcome at the end. All right, so this is a movie from one of our simulations that starts in a zoom-in region of cosmological volume. Typically, this is like 1 or 2 megaparsec moving and collapse. In this particular case, it's going to collapse to something like the Milky Way mass halo by redshift 0. So there are lots of progenitors that form in this region. And then if you look more carefully, the bluish magenta stuff is actually called ISM-like material. Green is warmish gas at around 10,000 degrees. Red is hot gas at around 1,000,000 degrees. So I'm going to play it one more time. Early on, galaxies collapse into these tiny objects, and each of these tiny galaxies are small dwarfs blowing their own bubbles of the winds. And overall, the formation of the galaxy is very complex. These bubbles interact with the infalling filaments, and they completely change the structure around them. Over time, the galaxy becomes bigger, and oftentimes, when there is an interaction or a large amount of gas infall, it triggers very large bursts of star formation. And by redshift of 2, we start having decent-sized galaxy. In this case, it's maybe 5 times 10 to the 9 solar masses in stellar mass, and it's growing quickly. And as you can see, the wind episodes are becoming weaker over time. There is the same feedback mechanisms, that winds do not go as far, and they are just in generally becoming a little bit weaker. And somewhere below the redshift of 1, these strong bursts of star formation that are triggering winds are basically dying off. So at late times, in the last 7-8 billion years, this galaxy switches to roughly continuous regime. There are small fountains that go to maybe 10 kiloparsecs, but they're not flying out towards the virial radius of this galaxy. And over time, galaxy is becoming much more coherent, and it's having this colder disk structure that increases towards redshift of 0. So the evolution at this point is that there are small fountains, there's star formation happening on the disk. Feedback regulates star formation within the galaxy, but does not drive strong winds from these massive halos. In lower mass galaxies, even at redshift 0, we still see some winds flying out of the galaxies and in closer to the virial radius. Right, this basically stays the same by redshift 0, so I'm just going to move on. So what can we learn from fire simulations? We have all this complexity. What can we actually take out and what we can figure out about galaxies? So first thing you notice in the movie is that star formation in fire is bursty. And this is especially the case in low mass galaxies and especially at early times. At late times in Milky Way size halos, it's definitely not bursty and it doesn't even drive strong winds. And these bursts of star formation drive strong gas outflow episodes. This is something that Sasha Murato will talk about in a couple of minutes. But I'm just going to show you a brief example of how these burstiness, inflow, and outflow are connecting in the evolution of galaxies. So here on the y-axis, we are showing the star formation rate, shown in black line, multiplied by a factor of 10, so you can actually see it on this scale. We are showing the outflow rate shown in red as positive velocities, and inflow rates shown in blue as negative rates. And we are showing the outflow at the quarter of the virial radius with this dashed line and at the virial radius with this dotted line. So you can see that the strong outflow episodes are following strong bursts of star formation. And only a fraction of the strong outflow that happens in inner halo actually leaves the virial radius. Nevertheless, the amount of gas that leaves the virial radius is still typically much higher than the amount of stars that form in the burst, especially in these low mass halos. You can also see that the inflow is shown here. It's much more continuous than the outflow, especially around the virial radius. But there are some changes to the inflow pattern closer to the galaxy at the quarter of the virial radius. You find that inflow tends to be affected by strong outflow episodes. It's temporarily disconnected. There are these brief peaks that drops to very low values. But then soon after, the remaining infalling gas and recycling of the outflows come back, and you have like mini bursts of the infalling material in between bursts of star formation. So there is this cycle of infall star formation outflows that are determining what's going on in the galaxies over time. So I'm just going to show this in a little bit more detail. So on this end, we selected one of the strongest bursts for this particular galaxy. And this is time 0 when the burst is starting. This side shows the outflow. This side shows the infalling material. And that's at time 0. This is at 50 million years, and this is at 150 million years after the start of the burst. So what happens initially, there is a strong inflow towards the galaxy. It supplies the galaxy with fresh material, but as the outflow starts, it can actually disconnect largely the inflow in the inner halo. It doesn't really affect the outer halo much. And soon after, the inflow reconnects to the galaxy and it supplies it again with lots of gas. One point I wanted to make here is that when you look at the net outflow and inflow rate as a function of the velocity of the material, you see some very interesting features. So again, here inflow is negative, the outflow is positive, and different line type shows quarter, half, and 1 virial radius. 1 virial radius is black, and quarter is blue here. And when you actually look, what's going on here is that inflow velocity is usually much lower than the outflow velocity. In fact, these two lines here show the plus and minus 1 sigma of the halo, so it's a little bit lower than VC of the halo. And the inflowing material tends to be just similar to the velocity dispersion of the halo, while the outflowing material typically moves with a factor of a few times larger velocity. And that's probably part of the reason why it's much easier to actually see the outflows in the real universe than see the inflow, because lots of inflow might be actually hidden close to systemic velocity. So again, I think Sasha might show a little bit more of this. So we can ask a question, how much material is actually expelled from these halos? Well, this is mass loading of halos, time average over all the bursts as a function of circular velocity of the halo. Black points here show the outflows around the redshift of 3. The blue points show outflows around the redshift of 1, while red ones are closer to redshift of 0. So you see that low mass galaxies and low mass halos have extremely mass loaded outflows, but this mass loading drops significantly towards massive halos. The dependence is different at the high and low mass end, but there is also a redshift dependence. Typical strength of the outflow drops with redshift. And it actually drops by only factor of few in dwarfs, maybe factor of 3 or 5 or so. But in the massive Milky Way size halo, it dropped precipitously. Actually, we mark these points as the upper limits because we don't even think that the outflows we are measuring crossing the quarter of the virial radius are related to star formation. They're probably just some strip material that is on elliptical orbits in the center of the halo. So late times, large disk galaxies in our simulations are basically lacking outflows. And that's probably connected to this buildup of these extended disks that we've seen in the movie. So we can look at what's going on in the CGM material around these galaxies. And again, we get to the interaction between inflow and outflow. And in this example, the dashed line is virial radius of an example halo at redshift 2, 3, and 4. These are the simulations without outflows, and these are the fire simulations with relatively strong outflows. What the contours are showing are the contours representing Lyman limit system absorbers. So you can immediately see that the simulations with outflows have much higher covering factor of Lyman limit absorbers in these simulations, and you can also see why. One reason is that filaments themselves are getting thicker because small galaxies are blowing them winds. And the second reason is that even the central galaxy, as it blows winds, some of the winds are contributing to Lyman limit systems. So I'm just going to show this small movie how this looks like. So we think that Lyman limit systems, Lyman limit absorbers in halos are actually connected to both inflow and outflow processes. And there are two effects how this strong feedback contributes by broadening the inflow region and directly by contributing to them. And the contribution of inflow and outflows to the total covering factor varies between 10 and 90% depending on the time. So we can also look at more details about galaxy populations, such as mass-metallicity relation. This is work by Shangsheng Ma, who's going to talk about escape fraction, completely unrelated work from this. So we find that fire galaxies reproduce the observed mass-metallicity relation. In this case, this is the gas metallicity at redshift 0 as a function of stellar mass. But they also reproduce the evolution of the normalization of this relation over time, which was typically a problem for many simulations because they had too much star formation early on. So we find that the normalization at 10 to the 10 solar masses changes by about the factor of by about a factor of 3 or so between the redshift of 3 and 0, and in terms of gas phase metallicity changes by a factor of 5 or so from redshift 3 to 0. So it's pretty encouraging that this more careful implementation of feedback can actually give us many of the properties of galaxy population that seem right. So finally, I just wanted to mention something that TK Chen will talk about, is the effect of feedback on the dark matter in these galaxies. So many people showed previously that strong outflows from the galaxies can gravitationally change the mass distribution in the center and modify the central concentration of dark matter. And we find that these effects are stronger at halo masses around 10 to 11 solar masses. So this is actually the slope of central density profile measured at around 1% of the virial radius as a function of halo mass. And these two lines show the NFW-like halos. So very small mass dwarfs, there is no effect of feedback. So ultra-faint galaxies, they're ideal place to actually figure out what kind of dark matter we have, because feedback doesn't play an important role because they form so few stars. But as you go to intermediate mass and massive, really massive dwarfs, then the effect of feedback becomes very, very important, and it peaks here around 10 to 11 solar masses. Then when you drop to Milky Way mass galaxies, the profile is again close to the NFW for complicated reasons that TK might mention. Interesting thing about this is that this might actually alleviate too big to fail, a problem pointed out by Mike Boyle and Colchin and James Bullock and others. So this is the example of simulations with stellar mass around 10 to 7 solar masses, ranging from a few times 10 to 6 to 8 times 10 to 7. And we have dark matter only analogs shown as dashed, and the fire simulation shown as solid lines. So you see that when you measure the circular velocity of the low mass halos at few hundred parsecs, the circular velocity is changing dramatically because of the effect of feedback. The changes are smaller for the lower mass halos, but they're bigger for massive halos, massive dwarfs. And in fact, the change is so big that it can bring you to close to the agreement with too big to fail issues. These points are representing measurements of the dwarf circular velocities from the local group. We cannot really solve the problem or claim that we can solve it because our statistics are really poor, and we need much more halos at these low masses, and that's why Mike, BK, and others are actually working on. So we'll see if this is going to hold on, but it's a promising way to address this problem. So I'm just going to read through conclusions here. FIRE uses physical stellar feedback model in cosmological simulations with few parsec resolution, without cooling prevention and without hydro decoupling. It regulates star formation within galaxies and the evolution of galaxies. It provides a good match to stellar mass-halo mass relation, mass metallicity, central matter density, and so on. And local feedback produces highly mass-loaded winds that lower galaxy masses and eject material into the CGM and some of it into IGM, that Daniel actually, I think, is going to talk about a little more. Inflow is more continuous than the outflows in all cases we look, but typically has much lower velocity, so it might be harder to pick it out when you observe galaxies. Some of the outflowing material can leave the virial radius, but large fraction stays and recycles in halos. And actually, Milky Way size halo end up with baryon fraction close to 50% or so, while dwarfs have much lower baryon fractions. So stay tuned. We are working on many different issues, and we are working also on the new stuff, such as more massive galaxies in massive fire, by Robert Feldman. We are working on Firebox, cosmological box with similar feedback, high resolution Milky Way, lots of dwarf simulations, new code, and so on. So that's it. Thanks.
Thank you. Questions?
In your mass loading as function of circular velocity plot, there is a kink, and it seems the kink is very stable over redshifts. I wonder what is causing the kink and why it's so stable.
Yeah, so there is definitely a kink somewhere here. This is kind of where we try to minimize the fitting on both ends. This is kind of where we actually get the minimum as well. I don't know if it's stable with redshift because statistics are pretty bad at late times, but we don't understand yet exactly what's causing the kink over there. So Sasha is looking into properties of winds, and we are trying to figure it out, but we don't have a good answer.
I mean, there's theoretical motivation for there to be a kink when you're transitioning between energy-driven and momentum-driven.
Sasha's going to talk about that in lectures after the second lecture after.
So what about AGN feedback, Dusan?
So at this point, unfortunately, we do not include AGN feedback. We are working on it and trying to figure out what will happen at around L star and more massive galaxies. We think that at least at these low masses that we can simulate now, AGN probably doesn't play a dominant role.
Do you have a ballpark that going for not dominant role, 10%, 1%?
I don't have a ballpark feeling. I would say it's probably, given that these are observationally, most of them are also star-forming galaxies. They are not completely quenched. They do have AGN in the center, but doesn't seem to provide very strong outflows, unless you go to very massive halos, the ones that Reinhard showed this morning.
Dusan, do you get thin stellar disks z equals 0?
So
that has been a problem in the past.
We don't have good quantification of the thickness yet, so we only have 2 galaxies at around 10 to the 12 solar masses and one at 7 times 10 to 11. And one of them, the one that I show in the movie, is actually disk dominated. The other one is bulge dominated. So we actually need to account for the details of this stellar disk there. I don't know the
resolution, right, to see a thin stellar disk.
So we should have few hundred parsec that we should resolve even at larger radii. Yeah.
Do you have an explanation for this sudden drop of feedback efficiency at low redshift in the Milky Way-sized halos? Do you have a theory?
We don't have good theory. Again, Sasha will talk about it. There are several things that are happening. One of them is that surface density of star formation actually drops to much lower level than initially in early galaxies. So this overlapping supernova effect is much weaker. We don't have so many clumps that are working together in driving wind. But there is also depth of potential well, because this is only happening in the most massive galaxies in our sample, and possibly other things that are making outflows disappear and galaxies become much more regular. So it's probably connected to surface density of star formation and the escape velocity, but we don't have final answer yet.
Dan, can the next speaker please get set up?
Question. Maybe you showed this. I might have missed it. Did you show us what the main sequence looks like? Its width, especially at higher redshift.
Again, given that we have several galaxies, I wouldn't comment on the width. At redshift 2, it seems to be close to the main distribution, but we might be a little bit lower at redshift 2 than the actual main sequence.
The problem is the width. You have periods where you're not making stars.
Yes, just switch.
Yes, so that depends what kind of observations we are using for star formation rates. So there is a postdoc that's working with Chris Hayward, and we are trying to see if burstiness of the galaxies actually matches the observed
Did you
burst.
still have a question?
So if you are measuring main sequence in H alpha, you're going to get bigger spread than if you are measuring it in UV star formation rate. So typical time spacing is, well, we can check maybe 200 mega years or so.
Dusan, I have 2 brief questions.
Right.
One is on the physics. So we found with the high resolution, like 1 parsec, that supernova feedback is sufficient without adding all these additional feedback on the molecular class scale, able to reproduce many things that you show as well. So you think in your simulation, if you drop all the other minor feedbacks, will supernova still be able to do it?
In the way we implement supernova feedback, it wouldn't be efficient to get the right stellar mass, halo mass in our case.
Okay. And then the second question is, seems like in your case, the structure is very sort of being disrupted periodically. Would that be consistent with Reinhard observations? You see a very organized disk.
So the movie I showed and the examples were about 1 or 2 order of magnitude lower mass than what Reinhard showed. We have a sample of galaxies in the massive fire from Robert Feldman that we're going to analyze a little bit more details to see if we are consistent with these very massive galaxies or not.
Okay, time to move on.
It's SPA, JMR, moving mesh, but it's very hard to see. So we also know that in order to produce realistic galaxies, infall is not good enough because it puts too much stuff into galaxies, and you end up with galaxies that are way too massive, and for the mass function that has very high low mass end and high mass end. So we need outflow of gaseous material from galaxies to regulate galactic growth. And outflows, on the other hand, are pretty easy to see observationally. We can see them at low redshift, such as this starburst case M82 in emission. And we can also see them observationally in high redshift in absorption lines. That's an example of stack profile of flat membrane galaxies at redshift 2.5, and you see blue shifted absorption from galaxies. So you see it all around, but it's actually pretty hard to model. You will see why. And the complication comes from the fact that outflows interact with the circumgalactic medium, and they do interact with the infalling gas as well. And they often recycle back into galaxies, as pointed out by Ben Oppenheimer and others. So to understand galaxy evolution, we need to simultaneously model gas inflow, gas outflows, and their complex interactions to figure out what exactly is happening and how do galaxies grow. So how to model star formation feedback in cosmological simulations? There's lots of text, but I'll guide you through it. We think that in low-mass galaxies, below about L star or similar, star formation-driven winds are the main outflow mechanism from galaxies. They likely dominate. The most obvious drivers that people talk about are supernovae, as pointed out by Avishai and others a long time ago. Jose Onyorbe, Robert Freca-Vandevort, and Daniel Angles-Alcazar. All right. So let's see what's going on with this feedback and what do we want to learn about it. So for a long time, I looked into gas inflow. And the reason that this was interesting, and it's still interesting, is that the inflow of gas from intergalactic medium is needed to supply long-term star formation activity of galaxies. And this inflow is naturally present in cosmological models, and we see it in all simulations. The only problem is it's hard to observe. And it can be in cold mode accretion through filaments, it can be cooling of the hot medium, and it can be complicated stuff. But nevertheless, we see it in all kinds of simulations. The problem with this is that at a typical resolution of cosmological simulations, supernova feedback tends to be very ineffective. It affects too much gas that is heated to too low temperatures, and it cools too fast without generating much momentum. So you end up having weaker feedback than you would like to just by supernovae alone. And there are two common methods to generate efficient outflow from galaxies to overcome this issue with relatively low resolution. The first one is so-called hydrodecoupling, in which we can implement winds by hand by literally just telling them how much mass loading they should have compared to star formation and tell them about the velocity they should be launched with. So this is clearly not predictive for the wind properties, but you might learn about IGM and properties of a galaxy as a population. These winds are then usually not allowed to
feedback in realistic environments.
All right, it's a pleasure to be here after 4 or 5 years again. And I'm going to be talking about Galaxies on Fire, where FIRE stands for feedback in realistic environments, as Joel said. And this is an effort with a large team. So this FIRE collaboration is mostly led by Phil Hopkins, Claude-André Foucher-Giguère, Elliot Quarter, and myself, and several postdocs and several students, as well as several close collaborators at CITA, Norm Murray, and at Irvine, James Bullock, and people scattered elsewhere. So I showed the pictures of people that either recently submitted or are about to submit papers related to our FIRE work. And this is Sasha Murato, DK Chen, Coral Wheeler, Cheng